Okay. Good morning, everybody. Hope you are doing well. You have done good in exam, I hope. Okay, in the name of Allah. So, what we have covered before, we talked about CPU performance. Remember? At the first chapter, we talked about CPU and what would be the main factors of the performance of a CPU. And we came up with CPU time. The time takes CPU to execute a program. That's the best performance factor that we could see. And when we try to analyze the CPU time, we came up with three main factors. Instruction counts, the program that you write has so many instructions. Then the clock per instruction, how many clocks do we need for each instruction to be executed? And then the clock rate, the frequency of the clock. So these three parameters make the CPU time. CPU time depends on these three factors. Okay. Then in the next chapter, we talked about instructions. We were saying that when you write a code in high-level language, this will be translated, compiled by a compiler to an instruction, to an assembly instruction, or better, to a machine code, binary code, zeros and ones. And this is the thing that the CPU will execute. CPU just understands these zeros and ones. So we write in a high-level language, then it will be compiled to machine code, and the machine code is going to be executed on the processor. We tried to, when we wanted to design the instruction set, for designing the instruction set architecture, we had some rules like making the common case fast, considering compromises, not making everything possible, not making complex instructions. So we tried to do some compromises for the instructions that we found out from the benchmarks that will be executed more, and we needed more. So we try to make them optimized, make them executed better in our process. And we talked about these instructions. So we talked about that MIPS has different kind of instructions like arithmetic, data transfer, logical, conditional branch, jump. These were all the type of instructions that MIPS had. And you saw that MIPS is some kind of a RISC architecture, reduced instruction set computer or computing. So it has a limited number of instructions compared to some other processors that they are somehow CISC processors. Okay? Yeah. You see how many instructions are there, and even you could see in the right column that how frequent each category will be used in the programs. So we try to make them, the common case, fast as much as possible. Okay, so we talked about this before in the chapter 2. In the chapter 3, we were going to talk about computing. How do we perform arithmetic computing, like add, subtract, multiplication? How do we deal with floating point numbers, not just integers? So that was the chapter 3. What I thought was that we can leave that chapter for now and go faster to chapter 4 and try to make the processor first so you could work more on your projects. You do have projects for building a processor, and then also you have labs. You can exercise these things in your labs, and then we will go back to chapter 3. Then today we are going to start chapter 4, the processor. Now it is time for us to build the processor. We have built the instruction set. We know how is the instruction set architecture. Now we are going to build a machine, a CPU, a processor, to be able to execute those instructions. That's what we are going to do. It is actually a very exciting task. I hope that you enjoy it, because you are going to build the processor, the MIPS processor, and it is the machine that executes all of the instructions. You write the code and give the code to machine, and it executes. I think it is very exciting. That's exciting for me, I hope for you also. So we talked about the processor. We talked about performance factor, instruction count. Instruction count, we talked about it before. I don't go through it again. It's determined by instruction set architecture and the compiler. We write in high-level language. Compiler gets it, try to make a machine code assembly out of it. So the compiler, the better compiler, the better code that we have, the number of instructions will be less. Or we can say it is executed faster. And also it depends on the instruction set architecture. It depends on the set of instructions that you have in the machine. So that's something that we talked about. Then we were talking about CPI, clock per instruction, and also clock rate, cycle time of each clock. And they are all determined by the processor, the hardware. These are determined by hardware. The first one, the first criteria, it's determined by the compiler and the instruction set. But now we have machine code, we have instructions to be executed, and the CPI, clock per instruction, and clock rate depends on the architecture, the CPU hardware that we are going to build. And this is the thing that we are going to do now. For implement MIPS, we start with a simpler version, which is not final, which is not real. In the real world, we don't use it right now because it has some problems. But to go to this topic, to start building the processor, we start with this version, a simplified version, and then we analyze the performance of this processor and to see which areas we could improve it, and then we will have a more realistic pipeline version of the processor. So in the first version, we build a single cycle processor. What do I mean by single cycle? It means that every instruction is getting executed in one cycle, and in each cycle, everything should be done, and then we move to the next instruction. That's the single cycle machine. It executes every instruction in a single cycle. The whole cycle takes to execute the instruction. But in the advanced version or the pipeline version, each instruction goes to the pipeline and it is executed one step by one step, and until it is finished. So we don't need the instruction to be finished in one clock cycle, but we need the instruction to be started in every clock cycle. This is very important. We talked about rates before. We compared Concorde with Boeing, if you remember, or Airbus. we told you that the total performance is more important just for one single instruction to be executed. So with pipeline version, what we think is that each instruction goes to pipe to be executed in every clock cycle. So if you look at the pipe, it means that the CPI is how much? The CPI is how many clocks per instruction do we get? The first instruction goes to pipe. In the next clock cycle, this instruction goes to the next level, and the second instruction comes to pipe. So what would be the CPI? Clock per instruction. Look at this. We had 2 clocks, we had 2 instructions. The next clock, the first instruction goes to the third step, the second instruction goes to the second step, and the third instruction is coming to the pipe. So again, we have 3 instructions in 3 clock cycles. So what is the CPI? 1. Clocks per instruction. We just consume 1 clock for every instruction, and that's the idea. So that's very good. In every clock cycle, we will execute 1 instruction, and that's good. Yes?
So are you basically just saying because we have 3 cycles for 3 instructions, you're going to have 1 cycle per instruction?
No. Yes. What I told you, not 3 cycles. Actually, the pipe might have 5 steps, 6 steps. I don't know. I am not talking about the pipe right now. But there is a pipe. Each instructions coming to the pipe in every clock cycle. So the 3 clock cycles that I told you was the total time that passed from the start of the execution. We had 3 clock cycles, and when we look at the pipe, we see that we have already started 3 instructions. So 3 instructions has been started in our pipe, and it just took 3 clock cycles. So it means that 1 clock cycle. So the 4th instruction comes, it goes to the pipe. The 5th instruction comes, it goes to the pipe. So in every clock cycle, it goes there. We will talk about the details later, but I just wanted to give you an overview of what is the difference between these two. But the first instruction comes to the CPU, it will be executed in 1 cycle and then goes out and the next one. So who could tell me what's the difference between 2? Both of them has CPI of 1. Every instructions takes 1 clock cycle. The first one, the instruction comes and it will be executed and completed in 1 clock cycle and goes out. So the next instruction comes. So what's the difference between these 2? Yes?
Throughput? The throughput?
No, the throughput is both of them are 1 clock cycle. The CPI is 1. In every clock cycle, 1 instruction is coming.
Yeah, but with pipelining, you can do like more instructions, right? And
more instructions? Yeah. Your program has billions instructions. So billions instructions coming one by one to the processor. So the throughput, not the throughput, the CPI for both of them should be 1. Yeah? Because the first version is single cycle processor. In single cycle processor, the instruction comes to the processor and it will be executed and completed in 1 clock cycle and then goes out. But in the pipeline version, every clock cycle we start 1 instruction, but we know that it is not being completed in 1 clock cycle. It goes to the next stage, and the next instruction comes to pipe in every clock cycle. So if we look at these 2, both of them have a CPI of 1. So what's the difference? Why are we saying that the second one is more advanced? Okay. So let me give you a hint, and you help me again, what's the problem. An instruction, let's say that we have an instruction of load word S0 with the address number. This is an instruction which should be executed. So in the first version, this instruction starts in the processor. So the processors look at the instructions, decodes it. Okay, it is a load. So we have to find the address. The address is the addition of S2 plus 0. We will find the address. Then we go to the memory, to this address, and take the data out of it. And then we take this data and put it in S0. This is how this instruction is executed. Okay? So in the first version, these things are going to be executed in one clock cycle. No clue? Yes?
Maybe the clock cycle is longer because there's more that the program actually has to do.
Yeah, lots of things that it do. But in the second version, we break up this. So for example, we say that, okay, this instruction goes to the pi. In the first stage, calculate the address. In the second stage, go and get the content out of the memory. In the third stage, bring that value and put it in the register. We broke up the same instruction into 3 stages. So this is the instruction which takes these things, for example, address calculation, then going to memory, then bringing the value and putting in the register. I say store register, not store register, register update. We will do these 3 things in this instruction. The first version needs to execute all of them in one clock cycle. So what would be the clock cycle? Would be something like that. Let's say it would be, I'm just putting a number. It's 20 nanoseconds. But the next version gets stages. So the first instructions come here, and it just, for example, adds to find the address. Then this instruction goes to the next stage, and the next instruction coming here. So the clock cycle of the next one would be this. Or we could say that the longest one of these stages, the longest one, okay? And you compare these two together, this, the whole thing compared to this, which is much, much faster. We will talk about it. So that in the pipeline version, we break up the execution to stages that the instruction goes to each stage. Again, if you think of execution time of just one instruction, they are the same. Or even the first one is better because there would be some overhead to passing this to the next stage. So even the first one is better for executing just one instruction. The time that instruction goes inside the machine and then coming out of that. Here, again, in the second one, the instruction goes to the machine and comes out of the machine after 3 clock cycles. So even they are the same, or even the second is worse. But the throughput is the main criteria here. We would like to have as less as possible. The CPI should be less. The CPI is important. How many clocks per the clock cycle here is more important. If our clock cycle is less, then it means that we need less execution time. Okay? So I just give you a brief introduction of what would be the versions that we are going to build. The first version would be a simplified version. Yes.
So are you basically saying with pipelining and instruction, it's going to take more clock cycles to compute a word?
To compute just one instruction, the execution time of one instruction. Yes, it might take more. Because I told you there are some overheads between the stages. Some minor overheads, it's not very much, but it is more than the single cycle implementation. Yes, for one, but it is not important. You have billions of instructions which would be executed in your program. So one instruction is not important. The whole time that we are going to see for the program is important. Okay? And to build this simplified machine, we start with a subset of instructions. We have different instructions that you know, even integers, even floating points, so many instructions that we have in our machine, but we pick a selected set of the instructions and we build based on that. But you learn, how did we build? How could you build your processor? So I saw that you have so many projects, we have many projects from you that you are going to build the processor to even modify the simple version of the MIPS. That's good. For example, we use as a candidate for the set, the limited set that we try to implement load and store. They are very important instruction. We pick arithmetic instructions, add, sub, and SLT, set less than. And we also pick branch and jump. So that's it. From the whole set of instructions, we pick these things, and they are somehow a good representation of the whole set. If we could build something for these things, then you could do it for the rest of the process of the instructions, and you could do the same. Okay? Okay. So, how an instruction is going to be executed? The first step. What would be the first step? Could you guess? Yeah, guess. Yeah, you. That's what your name, I forgot. Yeah, I knew your name. The lady in the front, white shirt. Okay, yeah, just guess.
I'm sorry, what's the question?
How do we execute an instruction? What would be the first step? What do you need to start execution?
Oh, you fetch the instruction from memory.
Perfect. So the first is first fetch. The second stage would be good. The next stage?
Sorry?
When you fetch instruction, then what do you do? What the processor do?
Do I need to read it from memory?
Okay, so that's the fetch. Read it from memory. The instruction comes.
So are you talking about like the fetch execute cycle?
Fetch, and then what?
Decode?
Decode.
Oh, and then execute.
And then execute. Yes, perfect. What was your name?
Michelle?
Michelle. Yeah, okay. Yes, so we need to get the instruction out of memory. We need to get it from memory. What do we call it? We call it fetch. When getting instruction from the memory, we call it fetch. When getting data from the memory, we call it load. So they are the same thing. We go to the memory and get something out of it. But in fetch, we get the instruction, and then the CPU executes that. But in load, we get a data and we do something with the data, add, and, or something. So Where do we fetch the instruction from? Please. Where do we fetch the instruction? Yes?
From the instruction memory?
Instruction memory. Okay. For if it is a memory, we need an address to get the data. What is that address?
It's like it's coming from the program counter plus.
Perfect. Program. So you knew everything. Program counter. So we need a register called program counter. We saw that in our instruction set. Yeah, we saw it here. That, for example, if you have a branch instruction, the PC is getting updated. And we talked about PC before. So we have a PC, program counter, which points to the memory location of the instruction that we would like to fetch. Okay? So the PC is a register. Do you know what is the register? You have heard a lot about the registers, yeah? In ITI 1100, you have seen registers, you have seen D flip-flops, yeah? Okay, are you okay? Yeah? I guess you had something in the first lab also about the flip-flops and registers and so on. So the register is a place that stores a value inside it. And you have mechanism to update the value and also to keep the value there without being modified if you don't want. So it keeps the value. A register is some kind of a memory. But when we are talking about the registers, we are talking about like flip-flops, that they are in the processor, they are close to the processor, and the access to the registers is very fast for the processor. But when we talk about memory, the memory is usually outside the processor, and then the processor should use its data bus, address bus, control bus to talk with the memory and gets data or stores data in the memory. But registers are very handy. They are at the processor. So we need PC. And as you mentioned, PC is pointing to a location of instruction memory. We have a memory of instructions that we are going to fetch from the and then execute. So that's so we go to the instruction memory, we fetch the instruction out of the memory. So the instruction, as we talked, it is 32 bits. So we got a 32-bit binary number out of the memory. Now processor should look at these 32 bits and tries to decode it. Okay, this instruction is somehow the processor understands that it is R format, for example. If it is R format, so the first 6 bits it's opcode, the last 6 bits are the function code, the next 5 bits is RS, the next 5 bits shows RT, and the next 5 bits is RD, and the next 5 bits is shift amount. Remember? So that was the R format instruction, for example. If it is immediate instruction, I format, then the processor should know that the first 6 is opcode, the next 5 is source, register source, the next 5 bits is the target, and then we have 16 bits of immediate value. If it is a jump J format, then the opcode would be 6, and the next 26 bits would be the address that we are going to bring to go there. The PC gets that address. Okay. So then we decode it, and based on the decoding, we know what to do. Is it R format add function? So we need to get 2 operand registers, add them together, and then store the result to the next register, to the RD register. We get RS and RT, add them together, the result goes to RD. If it is a branch, then we need to calculate the condition, compare it is either equal or not equal. Then so we have two registers. Again, we have to do some kind of calculation when it is compared, so we subtract them. And if the result is 0, then based on the condition, is it branch unequal or branch not equal, then we find out the target address, which is the immediate value, sign extended, and added to the PC plus 4, the current PC. Yeah, you follow? If you have questions here, it's good to ask, so you will review the instructions. And if it is J format, then we have just 6-bit of code, and then we have 26 bits. And with this 26 bit, we just add it, we just multiply it by 4, and then we get 4 bits from the PC, make a 32-bit value, and that would be the next PC. The PC would be this. Okay, so let's go and build. So PC points to some place in instruction memory, and we fetch from there. Then, based on the instructions, we see that there are different registers that has been used in this instruction. So, based on that, we go to a register file. A register file is a number of registers put together, and we either read from that register file or even write to that register file the new value of a register. We will talk about the register file more. So depending on the instruction class, as we talked, either we have to use the ILU to calculate, or for arithmetic like add, subtract, or and, XOR. These instructions has 3 operands, and we get 2 of them, calculating using ALU, the ALU, arithmetic logic unit, the unit that calculates for us, and then store the value. So ALU is used in arithmetic instructions, but it is not it. There are more use of ALU. We use it more. Where? Where do we use ALU? For example, in branch instructions, we need to compare 2 values. So it is not just the arithmetic result of a thing. And also for memory, when you want to calculate the address, because the address has a form of, let's say, an offset, like say 12, and then a register, like said S5, let's say. So the address is going to be calculated by adding 12 to the value of S5. So again, we need ALU to add these things together. And also to calculate the branch target address, because the branch target address is calculated based on immediate value plus, because it was a relative address, plus the PC. We have another type of instructions, another class of instructions, which are load and stores. In load and stores, we are going to get the data from the memory. Here again, we go to the memory and get it. Another type of instructions, they just update the PC, branch, jump. These 2 kinds of instructions, they update the PC based in the branch based on the condition, if it is taken or not taken. If it is taken, we update the PC with a new target address. If it is not taken, PC gets, like always, PC plus 4, the next PC. Okay, so let's start. This is the hardware that we are going to build. Let's look at these components first, and then we try to connect them, and then what does it do? if you look at here, this is the register for PC. So PC is very important, and it has its own register. So a register is dedicated for the PC. And as you could see, the output of the register is the program counter. And this program counter goes to instruction memory. And so let's say PC is 00A287 something. A 32-bit value goes to the instruction memory, and this would be the address. So when you have address for the memory, because this is instruction memory, we know that we just read from instruction memory. You don't write in instruction memory by your program. We write it, we load memory with something by operating system and these things. But in our programs, we don't write in instruction memory. Actually, we shouldn't write. So you see here, it's just reading. It gets address, and it will bring the data out of it. That's it. No need to write. Now, before of that, let me again talk about my memory for you, so you know what I am saying. A memory, when there is a memory, it has different locations. So depending on the number of the locations, we know how many address bits we need. For example, if this memory is 64K memory, it has 64K locations, how many address bits do we need? 2 to the something should be 64K. K is 1024, it is 10 bits. 64 is 2 to the 6, okay? 2 to the 5 is 32, 2 to the 4 is 16. 2 to the 6, so how many bits do we need? Yeah? For 1024, how many bits do we need? Yeah, you? 1024. 1024 is 2 to the 10. 2 to the 10 equals 1024. So how many bits do we need to address 1024 locations? Okay, let me ask you another question. We have 4 locations. How many bits do you need to address these? We have 0, 1, 2, 3, the address of these 4. How many bits do you need to represent 0, 1, 2, 3? 2. 0, 0, 0, 1, 1, 0, 1, 1. So how did you calculate that? 2 to the 2 is 4. If you have 8 locations, how many bits do you need? 3. 2 to the 3 is 8. If it is 64K, which is 2 to the 16, how many bits do you need? 16. Yeah, 16. So this memory, so let me clean it a little. So this memory has 16-bit address. Any questions? Okay, so this memory has 16 bits of address. A0 to A15. We can say A0 to A15. And let's assume that this memory, each location of this memory has 8 bits. Okay? 1 byte for each location. So how many data bits we get from this memory? It has 8 bits. So we would like to read and write 8 bits value to this memory. How many bits do we need? You should say either 8 or 3, because it is 8 bits. Somebody might make mistake and say 3. 3 is for the address. This is 8 bits, so we need 8 bits coming for the data. And it is bidirection. You see, for the address, I put one direction. For the data, I put bidirection. Why? Why a data is bidirection? Please? Yeah? Any guess? Yeah, you.
Reading and writing?
Yes, of course. Please contribute. Yeah, that's right. Because in memory, we read. So when we are reading, we are getting something from the memory. And also, we should write in the memory. We would like to write to update the memory. So it is bidirectional. What else? What else do we need in the memory? Anybody? Now we talked about reading and writing. Okay? So we need some kind of control to tell memory that, memory, I am going to read from you. Or memory, I am going to write to you. Yes? We need some kind of control pins, control data. So we have, let's say, read, control, and write. Write control. We have more things for the memory, which I am not going to read right now. Do you think of anything else right now? No? Yes?
I was just wondering, like, do the read and write inputs are they like select inputs?
Okay, that's what I'm going to talk right now. That's a very good question. But before that, do you think that we need anything else for this memory? We do have one more thing, which is called chip select, which I'm not going to read right now, which with this actually we select the memory, because in our design in a computer, we have lots of memories. And each time we are talking with one of them, not all of them. So we have to somehow select which one we are going to talk with it. So we have a chip select, which I'm not going to read right now. So address bus, here 16, data bus, here 8, read signal and write signal. Let me say the read and write signals are active low. So if the read is 0, then it means that we are reading from the memory. If the write is 0, then it means that we are writing to the memory. Now we go to the operation of read and write. How do we read from a memory? Okay, I wish I had some space. I go here, but it will be savvier, but I come back. So we have a memory, and we need to read from it. How do we read from memory? We would like to, for example, read from the memory address location 5 out of that memory. We want to read a byte from that memory. So I put a diagramming, a timing diagram for you, so you could it will make better understanding. So we had address bus. So that's not good. So let me say I add slides here so I could write on it. Okay. So memory. I told you we have address bus A0 to A15. We had D0 to D7, and we have read, which is active low, and write, which is active low. So how do we read from memory? If I want to read from location 5 of this memory, this is an example of 5. So if I put 5 here, it is just an example. What I do is that I first put 5 value on A0 to A15. 5. What is 5? 5 is this. 0, 1, 0, 1, and the rest 16 bits is 0. So this is 5. I put this value on A0 to A15. So A0 is 1, A1 is 0, A2 is 1, and the rest are 0. So this value is now put on address bus, okay? What then do I have to do? Yes, I put the address. I want to read. What should I do? I should make read active to tell the memory, okay, this address that I've put for you, it is for reading. I want to read from this location. So read, it was 1 inactive. At some time, we make it active. And write, it is not active because we are putting a read operation. It is not active. At this point, when the read gets low, it means that the read is active. The memory starts going to the location that we have specified and gets the content of that location and puts the value on its data bus. Up to now, what was the data bus up to now? What was that? The value, we don't know. But what is that? Are you familiar with tri-state logic? 0, 1, high impedance. No? Wow, that's too bad. Yeah, maybe I needed to talk about. Maybe I give you a video from my ITI class, so you just look at that for the high impedance value. That's that. But in high impedance value, it means that it is open. It is not connected to any. It is not 0. It is not 1. It is open. It is float because it is not 0. When it is 0, it means that the ground is connected there. When it is 1, it means that VDD is connected there. But when nothing, no 0, no ground, no VDD is connected, it is float on the air, it is nothing, it is open. So this here, is it 0 volts or 1 volt? Or 5 volts, for example? Do you know? What is the voltage of this? You don't know. It is open. It is open. It might have a potential over the ground of your circuit. You have a circuit, you have a board, and it has a ground. If you look at this compared to that, the potential might be something. Yes.
So you use the transition to basically avoid having a clock signal, right? Like for data.
Clock? Do you see clock here?
No, so like if you're transmitting data, for example, you can use it like that to avoid. I think I2C and CAN bus do it that way.
CAN bus is not for memory. It's for the peripherals.
No, but in general for communication.
Okay, let's move with this. Here you don't see any clock. Okay, because the memory doesn't have clock. The memory is some kind of a circuit, a design that whenever you ask it to start working, it works. So it starts working with that. But now you see that we have memories. You go and buy a memory, it says that the memory is PC 3000. So it means that it works with a clock of 3000 megahertz frequency. So what does it mean? We will talk about it later, maybe. And I don't know if it is reached in our course, but if you want, I will give you just a brief overview. But here we don't have clock right now. So whenever you active read, the memory starts working. Before the read, the data was high impedance. So it was not this. It was high impedance. I have to make it just open. It was open. So in the diagram, we show it by dotted line. So it means there is nothing there. It is not connected, nothing there. It is the pin at the memory chip, it is not connected, nothing there. But from the time that the memory, the read goes low, it starts to bring the value of that location and put it there. For example, let's say in the location 5 of the memory, we have a value of 20. So it brings 20 here. Now, if you look at D0 to D7, you see there is a 20 there. D0 to D7 is 20 there. And then you could take the 20 and do whatever you wanted to do with the memory load. Okay? So this is the timing of a read. The first thing is putting the address. The next thing is putting the read. Then we have to wait for a while here. We have to wait for a while after read is becoming active until memory works and bring the value to the data bus, and then we get the data. And what is this value? How many nanoseconds should we wait? It's written in the data sheet. You go to the memory data sheet, it says that, for example, read access time is 5 nanoseconds, for example. So it means that after read gets low, you have to wait 5 nanoseconds and then get the value out of data bus. So this is the read operation. Now let's look at write operation. When we want to write something in the memory. Yes?
So when you have a value for the address that like feeds into read?
No, the value for the address is just giving us the location. So memory looks at the value, it is 5. So it has 64K locations. So it goes to location 5 and reads the value there. There is a value there. It is a register memory. So, and then puts this value on the data bus. Address.
Read is it's just a completely separate function.
Yes, the address is just showing us the location. But in that location, there is a content, a value, which is the content of the memory. This content will be read and then put it on data bus.
Okay, gotcha.
So this is the read function. What about write function? Okay, let's write. Again, for write, what we do, we have a data, for example. We would like to write a value of 30 to the location of 10, the address 10. We want to write 30 to address 10 of the memory. What to do? Yes? We have to provide address. We give the address to the memory. The address is 30. And then, this time, we have to provide data before asking memory to start writing. So this is the difference. Here, first, A0 to A15. So we put the value of address, this is data that we are going to write. So the value of address is 30. We put 30 on address bus. 30, again, we can see what is 30. 30 is 16 plus 14. 16 plus 14, it means 8, and 8, 4, 2. So this is 30. Am I right? Yes. This is 30, and the rest is 0. So we put these 16 bits on the address bus. So address bus is now 30. And then, here is this important, we should provide data here at this time. It could be at the same time also, because memory doesn't do anything, we just provide the data. So we put 10 here for the data. When both of them are ready, address is ready, data is ready, then read is inactive, so it is 1. But write, when everything is ready, we activate write. So with this activation, memory finds out that there is a write operation going to be, should be done on the memory. The memory, when sees the write, it looks at the address, so it is 30, so it knows that it should go and write in the 30th location, and gets the value of the data bus, which is 10, then it writes 10 to that location with its mechanism, own mechanism. We don't go through the mechanism of writing or reading. So that's it. So for write, we put a write control to the memory, and for read, we put a read control. The whole thing that I've said was because of this. Here you see that this memory doesn't have read control and write control. Why? Because we're always reading from that. So whenever you put address here, it could start reading from that. It assumes that we are going to read, and which is correct. We are always reading from the instruction memory. So it starts the read operation and bring the value at its data bus, which is here called instruction. So the address gets from PC, and the value is the instruction, okay? So this is the first. This is the second element that we talked about it. Now let's talk about this. This is an adder, and it adds what value? The value is 4. So it adds 4 to what?
Program counter?
To PC, yes. So PC is coming from here. It was PC, yeah? You remember? It was PC. This is PC. So the PC is one operand of the adder, and the other one is 4. So PC gets added to 4, and here at this position, we have PC plus 4. So this PC plus 4 goes for the data of this register. Do you remember D flip-flop? I don't know, you said no or yes. But I guess you did it in the lab at least. So a D flip-flop has a data and has an output of Q. So whenever data comes in and we put a clock there, then this data goes to the output. We can say that it is stored in the register and it is available in the output. Yes? Follow? Is it okay? Clear? Register, D flip-flop. So you see here the value, the next value of PC, the next value of the PC. The next value of PC, which is PC plus 4, has been calculated and is ready at the input of the register of PC. So the next clock cycle, when the next clock cycle comes, this value would be the new PC. And again, this PC goes to instruction memory, brings the instruction out of memory, and so on. So this is the next PC that we calculate. Now let's go to the next element, which is very important. Actually, all of them are important, which is the register file. These register files, as we know, has 32 locations, 32 registers there, and each register is 32 bits, okay? For a moment, consider this like a memory. It is like a memory, but it is registers. It's close to CPU, it is very fast, but it needs address, it needs data bus to bring the registers, it needs control of read and write. It's like a memory. Consider it as a memory. But this memory is registers, flip-flops, fast, very fast, and it has a limited number of locations, 32 only, and each location has 32 bits. So consider this. So if this is the case, then we need address, we need read control, write control, and data. Okay. But this register file needs to do what kind of operation for us? Let's look at this here. Remember the instructions that we had? For example, in an R format instructions, we had 3 operands, RS, RT, and RD. So they are all from the register files. So we need to read register RS, please pay attention. We need to read register C, and then, for example, add them together, and the value should be stored in register D, RD, okay? That was the operation, the instruction. So if you look at this operation, and you know that we would like to execute the instructions in one cycle fast, how many reads do we need from the register file? How many reads do we need? How many? How many operands do we need to get from register file to add them together, for example? 3? 3?
What?
Are all of the 3?
Oh, add immediate?
No, add R formats. RS, RT, RD. How many do we read from the register? They are
3.
RTRS?
yes. How many? 2. We need 2 registers to get from the register file. 2 registers. How many do we write on the register? Just 1. Yeah. So it means that since we are going to do two reads at the same time, we need to get 2 registers. We need at least 2 ports for getting data out of the memory, out of the register. You see, it has 2 ports. These are 2 data bus of the register file for reading. And also, since we are doing so many things simultaneously, we have a different data bus for writing. You see, here we have 3 data buses, 2 for reading and 1 for writing. It is different from the memory that I showed you. So 2 ports, 2 buses for reading, and 1 for writing. So that's the bus, yes.
Excuse me. Are the 3 registers in there that it's the typical source registers and then the destination one?
Yes. S0, S1, T0, T1, A0, A1. These are the registers. How many were there? How many registers did we have?
4.
No, the total number of the registers. How many? 32. We had 32 registers. So we have 32 locations here. So if it is 32, you are the expert of the locations. If we have 32 locations, how many bits do we need to address them? 5. 2 to the 5 is 32. We have 5 bits because we have 32 locations. We need 5 bits to address these locations. And as you can see, we have the address here. Why it is 3? Because 2 of them are usually, not always, is going to be for reading from the register file, and one of them is the address of writing to the register file. And how many bits are they? How many bits? Each of them? They are 5 bits. Why they are 5 bits? Because we have 32 registers. So we have 5 bits of address. 5 bits. 5. And here we have 32 bits of data. 32 bits. 32. The data is 32, the address is 5. Yes?
So if we were to do something in I format, for example, there would only be 2 registers.
Exactly, yes. We will go through that because the CPU is going to decode the instructions. And when it is I format, it knows that in I format we have RS and RD. We don't have RT. Actually, we put RT, but the RT is the destination at the I format. So RS, for example, coming here, but RT coming here for the write. So that's the control that the CPU does. The decoding shows us what to go where, which bit goes to where. So that's something that we will see later. First, looking at the components, and then we will see how they work. So this is the next component. Now go to the next component. The next component is ALU, arithmetic logic unit. It does our operations like add, subtract, and, or, the instructions that you had, XOR, not. We had not also. Yeah, we had? No, we didn't have not. We had NOR. We had NOR in an instruction. So it does those instructions. So as you could see, it has 2 operands and it has 1 result. So 2 32-bit values coming to the ALU, and the result, a 32-bit value result, is getting out of the ALU. Okay, any questions? So this is the one, the next component. And the last there are another one there. So the next component would be this. As you could see here, it's written, it is data memory. And data memory will load and store, and it should have control, but because of the simplicity, I didn't put write and read here. For sure, it has write and read control here. But again, it is a memory. So it has address, it has data, it has control. So the address is coming, as you could see, the address is coming. The address is coming from here. We will see why the address is coming here. We will see. You could guess, because the address is going to be added displacement plus offset plus the base, and then that would be the address. So that will be calculated in ALU. So the ALU gives us the address. And we have data. If we want to write on the memory, the data coming here, and it is been written in the memory. If we are loading from the memory, the data is loaded here, and then it goes wherever it should go. So this is the data memory. Address bus, data bus, control bus, which I have not put here. Now let's, okay, there are one more components that we talk about. This one, it is left. So what is this? Who could guess? What is this? What is left? Yes?
Is that going to be responsible for updating the pointer for the program counter?
It is, because it goes there. But what does it update? Because we have PC plus 4 here. So what is this?
It looks like it's adding the new value of the program counter with the address instruction or the address location.
With address, something coming from here. What is that? What should be? What is in the instruction that we get it and then add it to PC to calculate the new PC? Which instruction?
Load?
Load is from memory. Load gets its data from memory. In load, we just calculate the address and then going to memory. You should do more exercise on these instructions, and for each instructions, see how this works. So it will be your exercise, your homework for the next session. Go through this and try to see each instruction does what with these components. This is for calculating the target address of the branch. When you have a branch, then there is an immediate value, the offset, which should be multiplied by 4, and then a sign extended, multiplied by 4, and then added to PC. And this would be the new target address. If the branch is taken, this would be the new PC. If the branch is not taken, this would be the new PC, the calculation here, okay? So we have calculated both, if it is a branch. If it is a branch instruction, we calculate the new address, the new target address, or the regular target address, PC plus 4. And depending on the outcome of the branch, it is either taken or not taken, one of them would be the next PC. Okay? So we have talked about everything, yeah? Everything is covered? Instruction memory, PC, register file, ALU, data memory, the adder for PC plus 4, the adder for branch target address. Okay. But there is one thing that first I have to mention. In hardware design, you cannot connect two wires together for one point. Could we? There is a conflict. You cannot drive this and put them in one location. It's not possible, you know, because some of them might drive 0, the other one might drive 1, and that's too bad. And do you know, it is another question, not for the course. Do you know what would be the value of that point when there is so many drivers coming to that point? The value of that? You were not familiar with tri-state, so that should be the next one. We have actually 4 value logic in hardware. It is not only 0 and 1. 0 and 1 is very simplistic way of looking at the bits here, of the pins here, of the wires here. But we have 4 values: 0, 1, high impedance, which we call it Z, and also X as unknown. When you have 2 drivers going to somewhere, it might actually blow out the circuit because it might get a short circuit here, you get lots of current, and it will become more hot, and so it blew. It might do that, but even if it doesn't do that, we don't know the value. Is it 0 going to be forced this position to get 0, or is it VDD which brings this location to VDD? So we don't know. We call it X, and it is very useful. When you do simulation in your Quartus, have you seen the simulation waveform before setting the values for the wires? What is it? It is X, because you haven't set any value. It is X. And then you start putting values there then it gets 0, 1, or maybe Z. Maybe Z. I don't know if you have come up with Z or not. Maybe we have to give something for the lab. Okay, what I was saying, that we cannot connect these two together here. So what to do? You should know of a component which is selecting two things and putting it to the output. What is that? You should know that. The component that selects two things, for example, out of two things, selects one of them.
Use an OR gate.
So you are going to the low level of OR, but before that we name a component, a higher level component.
Multiplexer?
Multiplexer, perfect. We should talk about in RT level, not just relay. It is a multiplexer. So we need multiplexers, and there are a lot of locations that we need multiplexer. For example, here is 1 point. Here, okay, here. Again, you see coming here, so both of them goes here. So there we need a multiplexer here. What else could you, here? For example, here. One coming from here, the other coming from here. So we cannot drive two things to one location. So we need multiplexers for all of these things. So this cannot happen. They are invalid. So what to do? We put multiplexers. So now the circuit is better. So here, for example, we have calculated the address, target address here, the PC plus 4 here, and based on the outcome of the branch, which is either taken or not taken, we select. So the select of this multiplexer is coming from the outcome of the branch if it is a branch instruction. If it is not a branch instruction, this selects always 0, so it selects the PC plus 4. But if it is a branch of instruction, so the select is coming from the outcome of the branch. So this is the select of the multiplexer. Here, we have a multiplexer. So I go through the detail of this. How to select from this one or that one to store to write on the register file. Because we have two instructions which are going to update the register. One is an R format instruction. For example, if you write add S0, S1, S2, then S1 and S2 will be added, and then S0 is updated. So we have to have some kind of ALU result going to register file to be written on the register file. And also, the next instruction which updates the register is what? Who could say? Could we put bonus for that? Whoever says the first should get the bonus. Which instruction, in addition to R format instructions, updates a register? You could see it here. Yes?
I format?
No, it is the I format for if it's I format, but I need the instruction. Which instruction? Yes?
Add I?
Add?
Add immediate?
It is again arithmetic operation. No, arithmetics add and or, yes, they are coming from here. Add I is coming from here. The result of ALU. Yes?
Load?
Load, very good. The load gets the data from data memory and puts that in the register. For example, load word S1 with an address. So when we get the value from the memory, we will update S1. So please remember to post there that you got the bonus. It will be added to your final mark. Okay, so that's it. Maybe it's enough or it is already gone. So let's do the quiz. 1 minute. The quiz of 1 minute. Content. Attendance. Okay. This ended. I have to. Very complicated. So So please go to the quiz attendance, and then the password is 0623. We are now 9:55 a.m. Hope it's good. Now refresh and press. I hope it works. Is it working? 0623. Okay, perfect. Thank you very much. Have a good weekend. See you on Monday. So as a homework, please look at this and each instruction, see which part of these components are going to work for the execution of this instruction. So that's your homework. It's important.